I want to tell you about some things that we're doing in the RISC-KIT project, which I'm coordinating, and there's a lot of people from the RISC-KIT project here in the audience, but I also want to give you some examples of early warning systems in the USA and the Netherlands. And there are many other early warning systems, but it's about the general concept and where things are going. My name is Ab van Dongeren. I work at Deltares, which is a research company in the Netherlands. I prepared these slides with input from a friend of mine, André van der Westhuizen, who is at NOAA, which is the National Oceanographic and Atmospheric Administration in the United States. Piet Harens of IMDC, which is a partner in the RISC-KIT project, but also in the MICORE project, and Simone de Kleermaker, a colleague of mine, who's an expert on FEWS, flood early warning systems. We started the project RISC-KIT with the notion that there's been a couple of recent and also historic low frequency and high impact events, like the Xynthia storm or the Xavier storm that only last year. The Xynthia storm happened a couple of years ago in the Vendée in France. And that demonstrated once again that Europe is under coastal threat. And these things are only going to get worse because, let's see if I have a pointer. The risk is going to increase because the risk is combined, probability of hazard and the consequences. It's almost similar to what Louisa was showing. Consequences can be exposure and vulnerability together. Probability of the hazard, so the probability of flooding is likely to increase because of climate change, increased winds, extremes in rainfall, increased storminess, increased sea level rise. But even if that doesn't happen, which is still likely to occur, the consequences are going to increase because of increased coastal development. So there's simply just more investment on the coast. So the risk is going to increase. And this necessitates an adaptation to climate change. Because the IPCC for the European continent in their assessment report 5, they estimated that flood damage on the European coast will increase to 11 billion euros per year at the end of the century. And the IPCC says that solutions on the coasts are feasible, but they're expensive, but not as expensive as this. And the other thing is that they're conflicting with other land uses. So how bad is it? So we looked in the MICORE project, we looked at how many disasters occurred and how they were grouped according to hazards. So if you look at storms and you look at floods, they make up the majority of the events. They also make up a good number of the fatalities, but some of them are even higher. I think this is due to the 2003 heat wave in France and Holland. So, but in number of events, it's quite remarkable how big the effect is. So IPCC in 2014, they identified 3 key risks to climate change for Europe: floods, droughts, and heats. So, and this is one of the charts from that report, which I borrowed. And it's interesting in the floods business, which we're in, what they're saying is that there is a high confidence, they have high confidence that the risks will increase, like I just said. The hazards are going to increase and the consequences. They're also saying that there's high confidence that adaptation measures can be taken, so things can be done. But it will cost 3.5 billion euros per year by the end of the century. It's a lot less than the 11 billion in damages, so it should be an easy solution or an easy choice to go for this, but still that money needs to be put up front. The other thing is that there is conflicts in land use and environmental damages that may occur. So the coast is already developed. How are you going to adapt on a developed coast, like you have here in Tuscany and in many other places around Europe? And the other thing they identified is that there are a lot of regional differences in approaches. So this is what we're trying to address, partly in the RISC-KIT project. And if you look here, this is the risk in time. So this is the present risk. And you see that it increases from medium term to long term. And the dashed lines are what we can gain by taking these measures. So there is a lot of risk reduction possible here because we can get rid of the shaded areas and go back to the solid bars. So the risk is still going to increase, but we can reduce the increase. So this necessitates a re-evaluation of coastal disaster risk, and we need to find new disaster risk reduction or DRR strategies. And those strategies consist of a mix of prevention, mitigation, and preparedness efforts. So this is a classical separation. Prevention is outright prevention that a flood will happen. So for instance, dike protection, like we have in the Netherlands and like you have in the Po Delta. Mitigation is, for instance, limiting construction in flood-prone areas or putting houses on elevation, as happens in the United States. And preparedness is, for instance, be prepared, and you can do that by implementing early warning systems, or EWS measures. So this is highlighted. This is what I'm going to be talking about a little bit more. Because these early warning systems are in place, and what they do right now, mostly they provide information on time so authorities can act about hazards like water levels and wave heights. And if you combine that with your knowledge about the environment and the topography of the coast, you can issue warnings. So if a water level goes above a certain level, then you can issue a warning and something can happen. And what you can do with early warning systems, you can evacuate people and cattle, like we've done in the Netherlands in river floods in the mid-90s. You cannot really protect housing, so you can do a little bit. You can implement emergency flood defenses, like flood walls, based on these warnings. As of now, these early warning systems, they are implemented a lot in river basins, so for river floods, but not so much on coasts yet. There are early warning systems here and there. I'll give you a couple of examples. But what they all do is they give a prediction for the storm surge levels, and sometimes wind, as in France, and sometimes, but not very often, wave height. Mostly it's about storm surge levels. What's not taken into account is the morphological change, so the fact that a coast will erode while the storm is hitting the coast. And if a dune is eroded, it can breach, like we saw in the example that Louisa showed. There can be breaches in the dune system, and floods can still take place. So if you want to have a proper warning, you need to take this effect into account. And furthermore, what hasn't happened yet is that there's no link between the hazard, so the hazard of water levels and inundation, to the impact, so the consequences. It's actually the same word. So how does it affect people and how does it affect property? So you need to go from the natural hazards to the socio-economic impact. And if you combine those two hazards and consequences, you are at the level of risk. And Louisa showed how they're approaching that for the flood directive, but they're still in the first stages. So I have some examples from the USA, from the Netherlands. USA is about hurricanes, what I'm showing. The Netherlands is about storm surge due to high winds. Some developments that we are undertaking and the way forward, what we're doing in the RISC-KIT project. So this is an example from NOAA, actually the National Hurricane Center. What they're moving to is prediction of surge levels. If you look carefully, here you see, this is the northeast of the United States, this is New York, and this is a simulation of Sandy, and what you're seeing is water levels. It's the surge due to the wind, but also the tide. So here you see very high water levels. This is the Bay of Fundy, this is normal, but here there's high water levels because the hurricane is coming, and this is a running, we wait for it. I think the hurricane is coming here. So this is the eye of the storm, you're probably familiar with it, and it went to the west and it hit the state of New Jersey. And it's coming here, and you see high water levels around New York. So this is what they're working on, high computing, computer-intensive codes, numerical codes to compute the surges. And what they get out is a number of products, as they call it, number of warnings. And this is one that's used very often, and it gives an estimate of the exceedance level of the water level. So this is a 10% exceedance of a certain water level. So here in light green, this is a warning that there's a 10% chance that the water level will exceed, and this is in feet, it will exceed 7 to 9 feet, so 3 meters. You have to divide by 3. And here it's a little bit higher in this estuary or this embayment called Long Island Sound. So this is actually really for the experts, because people on the ground, yeah, what does it mean? How does it really cause this to flood my state? So these kind of products, the typical prediction, 10% of the exceedance level, it's not very intuitive to interpret. And furthermore, it gives no information about flooding, damages, and vulnerability. So that's the next step that needs to be taken. And in fact, at the National Hurricane Center, they are doing this. This is an example, an experimental storm surge graphic of inundation of a coastal city in the United States. This is Fort Myers in Florida. It's on the west coast of Florida, so Miami is there and then Fort Myers is here. And what you're seeing is how deep the inundation will be. So red are deeper areas of inundation and all the way up to blue. So this gives already an overview about what you can expect in a certain neighborhood for flooding. What it doesn't say is the duration of the flooding, because that's also important. And the other aspect which they're working on is to integrate this with socioeconomic aspects. So the social part, which areas are more vulnerable to flooding, because some areas may be very resilient, people can evacuate easier, but there could be neighborhoods with older people or younger people that cannot be evacuated easily. So even if you are, if those neighborhoods are in blue, you can still have more damages there, where the houses are less well built. So those are things that you have to take into account. So here they're already starting with a combination of a hazard and topography, and then you can go to inundation, and like I said, the next step is to add social vulnerability to the prediction. So that was the United States. In Holland we have a similar system. Of course, this is the Netherlands, this is England. Our storms are mostly coming from the northwest and from the southwest, but our highest storms are actually coming from the northwest. And now we have a whole model system based on Delft-Fuse flood early warning system that predicts the water level along the Dutch coast. So we're getting graphs like this. And this is an animation, if I can run it. Not very exciting, not a real storm, but what you see is the water level here. So this is the tide, these are the waves that we have added, so this is new, and this is the wind that's driving it all. So you start with wind, then you get the waves, then you get the water level with the tides. This is for 3 days in June. There's no emergency, very calm seas, but it's an animation that I found that we could use. So what we're doing with this system is we issue warnings, and the way it works in Holland, we have a lot of dikes, levees, and we get a prediction of a water level. So this is like the tide goes up and down. And then there are different warning levels. We have a pre-warning level, a full warning level, and an alarm warning level that our water boards use to start ramping up the alarms, to start inspecting levees, to maybe evacuate people. So the pre-warning level, just the whole operation starts to be put into place. Everybody is called up, everybody is called back from vacation, and they need to be at the ready. And then when the warning level is hit, so that's 3.5 meters above mean sea level, then there is full dike warnings. People are actually on the levee, watching the water, seeing that the dikes are not being breached. And alarm level is when people are actually evacuated in certain areas. So you see that the accurate prediction is very important, because what the authorities do is based on if this line, this prediction, goes through this ceiling or this line or this ceiling, and if we miss it in the predictions, then the authorities make the wrong decisions. They either don't go out or they go out too soon. So you have a false warnings. So that needs to be improved. And what we're doing is we're doing a lot of calibration and validation. We do that with more and more with satellite data to measure the tides. But we also have 100 coastal tide observations, not only in Holland, but all along the North Sea, where we're working with the other countries around the North Sea to improve our models. And we calibrate, so we make the models more accurate automatically with advanced tools called OpenDA. And while the storm is coming, we also use data simulation. So we take data in as the model is predicting the water level. And if there's a mismatch, then we tune the model. So let the models be steered by the data. The data is telling what's going on, and we can adjust the model predictions accordingly. What we need is lead times up to 15 hours, so 15 hours before the authorities need to know what's going to go on. And with this effort, we've been able to reduce the errors along the Dutch coast significantly. So we're down to tens of centimeters in high storm surge situations. So that's what's going on, but still, almost everything is focused on water levels, storm or hurricane water levels. And what we need to do in the future is to include more hazards. So we need to go to multi-hazards. So we need to include waves and wave effects. We need to include flash floods from the land. And Nicola Rebora will talk about that. So it's not just a marine thing, it's also a land-based flooding or flooding that comes from the land is important. Not so much in Holland, but in other places like Catalonia and here in Liguria, it's important. And like I said, the morphodynamic change of the coast. So the fact that the coast is changing while there is a storm is important. And I'll have an example in a second of where you see that it's important. We want to add more hazards, but then we also want to go from hazards to risk. And you have to do that by looking at vulnerability. So we need to include vulnerability to come to risk. And that makes a true assessment of risk possible. And Christophe Villavaten is going to be talking about that later today. So what we're doing is we're building an early warning system for the coast in this project. We can use it as an early warning system, but we can also use it with hypothetical storms to already evaluate what DRR, what disaster risk reduction measures are feasible and effective. And we're building on a Delft-Fuse software that was actually developed for rivers, but now we do it for coasts. And we have flow models, so that do surge, we have wave models, and we have these morphological models, and they're all linked together. Results are stored in a Bayesian belief network. I'll show you an example of that, so that we can store a lot of our information beforehand, so you don't have to run the model while the storm is happening. And we're doing this in this project on all different sites. I'll show you those in a second, but our different partners have different models. We're not using only the Delft models, but we're also using all kinds of other models which are now linked into this Delft-Fuse system. So it's a very open system, and people are using made adapters to link their own model into Delft-Fuse. And we have our final workshop on that next week. So we're doing this for 10 sites in Europe and one site which Paolo is working on in Bangladesh. And of course we have two Italian ones. One is Porto Garibaldi. Dr. Cevola is also working on that. Nicola Rebora, Dr. Rebora is working on Boca di Maga, which we discussed yesterday a lot. And then there's a number of other sites around Europe. And they're all very different, so it gives us an idea of how effective this modeling tool is and what the pitfalls and what the gains are that we can have. So we have a Swedish site in Kristianstad, a very low-lying area in Sweden. We have a fjord, which is a big estuary in Kiel in Germany, an open coast in Varna on the Black Sea. We have the Tordera Delta in Catalonia. We have a barrier island system in Portugal, the Ria Formosa. We have the open coast or the estuarine coast in La Faute-sur-Mer, which breached in the Xynthia storm, a harbor in Zeebrugge in Belgium, and a marshland area in North Norfolk in England. One example of how this works is from one of my students. We didn't look at the European case yet, but with the USGS, the US Geological Survey, and the Corps of Engineers, we looked at the breaching or the inundation of this neighborhood in New York City called the Rockaways. And Carl Nordstrom showed that a little bit yesterday. So this is Manhattan. And then here's the airport, John F. Kennedy Airport, if you've ever been there. And then here is a low-lying barrier island, which is completely urbanized. And it got the full force of Hurricane Sandy. So this is an outline of that barrier island. You see the streets, you see houses. We had a lot of information about damage down to the house level. We know what the damage is to each house, and what we try to do is we try to correlate the inundation of the island and the flow velocities to the damages found on the house. And we got pretty good results. So if I show the animation, what you see here is a transect. So that's a line from here, from offshore to onshore, a cut through of the island with the water level here. And here you see the top of the barrier island. And this is the storm surge from Hurricane Sandy in time. So the storm is coming. And what you're seeing here, this is a morphological model. So there's waves hitting this dune area. You see some changes occurring here. The dune, which is not very big, is eroding. And that's the key to the problem, because the dune is eroding and finally it's being washed away and overtopped. You see that here, the whole place flooded. Our prediction is fairly accurate. And you see that the whole place flooded, and we're collecting how high the inundation went, what the flow velocities were, and we're correlating that to the damages that occurred with reasonable skill. Not 100%, but about 40%, which is much higher than the industry standard. So these computational runs are very expensive, but what we can do is we can store this information, this combination of the water level, the waves, and the damages into what's called a Bayesian belief system. So this is going to be very complicated, but basically what we have is a system where we look at the storm characteristics. So this is a wave height, water level, and we combine that with information that we have about the land use and the density and where the houses are. Those two together with the flow velocities and the inundation on the island can give us estimates of what the housing damage is, what the mortality is, and what the ecological impact is. So, and then you see these distributions. This is still a mock-up. We're still working on this. But what you can do is you can say, okay, if I have a certain elevation or a certain storm duration or a certain wave height, how does that translate to mortality, and how does that change to housing damage? And if you say, okay, that housing damage or that mortality is not acceptable for this wave height, what can I do to change that result? So how should I move people? Should I move houses? Should I build a higher dune? Those are all kinds of games that you can start to play with this model. That's early going. This is a PhD student at TU Delft that's working on this. He provided me with his graph. It's still early goings, but it's something that we can use across Europe. So, in conclusion, if I go back to the early warning systems that we have in place right now and operational on the coast, they're mostly about water level, so single hazard. We need to go to multi-hazard, so inundation, flow speed, coastal erosion, wave impact, but also from different sources. Marine, flash flood, direct rainfall, which we're actually not addressing as of yet, but it's going to become important. And then what we finally need to do is connect all those hazards to impacts to be able to make informed decisions about how we should change the infrastructure or the protection of our coast. Thank you.